Actually, this is the third day of training and fifth technical session of this training program. The topic is crop yield modeling under different climatic scenarios using APSIM. Today we have with us Dr. N. Subhash sir. Let me take an opportunity to introduce our today's resource person, Dr. N. Subhash sir. Actually, Dr. N. Subhash sir presently working as a principal scientist in agricultural meteorology at ICR, Indian Institute of Farming System Research, Modipuram, Meerut, Uttar Pradesh. He has joined Agricultural Research Service in 1997 as a scientist at ICR Research Complex for Eastern Region, Patna, Bihar. He did his MSc in Meteorology from Cochin University of Science and Technology and PhD also from same institution with topic entitled Drought Climatology using Remote Sensing and Crop Growth Simulation Models in IGP. He is having more than 100 publications in peer-reviewed national, international journal, which is having high impact factor and NAS rating. He has worked as a lead principal investigator of agriculture modeling intercomparison and improvement of ICR collaborative project, ICR ICR University of Nebraska, USA, collaborative project on yield gap atlas NICRA project. He developed Excel-based software for estimation of greenhouse emission from integrated farming system. He visited more than 20 foreign countries and provided in provided invited talk in American Society of Agronomy, American Geophysical Union (AGMIP), and GYGA Global Workshop, etc. At present, research areas including impact assessment of climate change, impact at household level using multi-model measurement of greenhouse emission from IFS, Agroadvisory Services, in addition to meteorological studies. Sir, it is honor and privilege for me to welcome to you, sir, on behalf of organizing committee and participant. So, Subhash sir, welcome once again. And now I hand over virtual platform to Dr. N. Subhash sir. N. Subhash sir, please.
Okay, thank you, Dr. S.P. Yadavji, for giving nice introduction about me. And good afternoon to all. First of all, I would like to extend my sincere thanks to Dr. Manoj, Head Department of Agriculture Meteorology, and other faculty members for providing me the opportunity, and also the Department of Agriculture Meteorology, as well as NAHEP, CAAST, and for giving me this opportunity. And also I am thankful to our institute director for allowing me to give this invited talk. Let me share my screen, just 1 minute. Is it okay?
Yes, sir.
Okay.
Okay, it is okay.
Okay. So myself, as mentioned by Dr. S.P. Yadav, myself, Dr. Subhash, Principal Scientist in Agriculture Meteorology, and the topic assigned to me is crop yield modeling under different climatic scenarios using APSIM. And my outline of presentation will be, first I will tell you what is modeling, why do we want to model things, then introduction to the APSIM cropping system model and its scope, and how this testing and validation of protocols, and what is the introduction to scenario modeling using model to answer what if questions, that is scenario analysis, and also some of the examples pertaining to use of these models and its applications, and some of the work we have executed at IAFSR, that is particularly using the APSIM model, that is SARC Australia project, ACME ICR collaborative project, and NICRA, as well as GYGA Global Yield Gap Atlas. And these results are available in the public domain also. And First, I will tell you what is the definition of a model, because we will talk about APSIM model. First, I thought it is better to give some introduction about the model. So you see, any system, any real system, we can represent through different mathematical equations or pictorial representation or conceptual framework or physical model. So any system, any real system we can represent by a set of equations or a single mathematical model, like that we can represent. So basically, the mathematical model means any system can be represented by a set of mathematical equations, particularly with respect to time or space. Normally, you see y is equal to ax plus b. That is a simple the straight line equation. That line, each line we can represent it by mathematically one equation. Like that, in agriculture, we can represent anything. That means from seed, how it is going, how it will interact with the soil, and after that, after germination, how it will grow under different complex situation. We can represent each processes in different mathematical equation with function of space, function of different variables. That way we can represent anything in mathematical equation. That is a model. Then, why crop simulation models required? You see, a crop simulation model is a simulation model that describes the process of crop growth and development as a function of weather conditions, soil conditions, as well as crop management practices followed. Like that, we can represent. And basically, you see, these are the complex processes. There may be interaction between different processes. So it is complex processes and also the complex interactions. We can create a virtual agricultural system in the computer. But you will remember, this is not a replacement of field experiment. This is simply a tool to represent the system, and we can use this system for different scenario analysis. We can use, you see, these are the different models available. One is APSIM, it is developed by Australian group, then DSAT by USA, then Infocrop by our IRA, and WAFOST, that is the World Food Studies model by the Netherlands, Wageningen University, then another model, STIX. These are some of the models I have mentioned. There are several groups working on this. And you see, you see why we need the modeling, why we need the simulation modeling. You see, all farming systems are experiencing high level of adaptive pressure because there is competition among the different uh, activities by different resources for resource sharing. You see, because of this, the changing weather patterns, that means some less years, some less rainfall or more rainfall in particular years, then change the temporal distribution of rainfall and less stream flow and increased temperature as well as decreased temperature, then increased carbon dioxide and increased evaporation. All these changing weather patterns, then competition of water between agriculture and other users like industry, growing cities and this, and changing market focus. So commodity prices will also fluctuate. Then different environmental drivers are also there because you see other externalities will be there. The overriding need to produce more food. Our main purpose is we need to produce more food to feed the growing population. For that purpose, this simulation modeling is a tool to represent the system and to find out some scenario analysis. Then there is a need to evaluate potential new farming strategies because we need to test different management practices or farming strategies. We need to conduct experiments. It is very difficult to conduct the experiment for all purposes. We can conduct some experiments and we can use that data set for modeling so that we can conduct scenario analysis. So not just crop alone, but as part of diverse farming system. Because initially we thought everybody is talking about crop or single crop, single commodities. But nowadays, this cropping system or farming system, we need to see the modeling, how we can model the system as a whole. Then, for example, you see under changing climatic scenarios, how the water resources, because different cropping enterprises will be there. So, how these limited water resources can be shared among the different cropping enterprises that we can model. And also optimizing the agronomic management of rice or other crops in rotation with other crops and pasture. So we can, one thing is, suppose you have, for example, suppose you have rice wheat system already growing in one area. So you want to introduce one crop after rice wheat system. Is it feasible or not? We can do the modeling analysis. We can see which variety is suitable for Kharif season, which variety is useful for the Rabi season, and after these two seasons, how many days you will get to grow, to introduce some new crops in that particular region, and how this crop will take the nutrient uptake from the soil, and how it will respond to the weather parameters. Like that, we can do the modeling aspect. Then assessing different crop residue management practices between or within the crop to conserve water and increase soil fertility, how the soil fertility will decrease or increase according to the crop residue management practices, that also we can model. And optimizing the management and timing of one crop to facilitate enhanced performance of another crop in the rotation. That means how we can, suppose crop modification, crop sowing, how we can modify the soft growing schedule, particularly the schedule, how we can modify the schedule or crop calendar. That way, this modeling tool will be helpful. And how do the range of potential adaptation ideas compare? Because we can suggest these are the potential adaptation package for that particular area. We can test these potential adaptation ideas are feasible or reasonable in that particular soil, particular region, or different varieties and different management practices that we can test. And well-tested cropping system models can play a big role in developing solutions to this problem. And but we will be, you see, we should think about they are not a replacement, as I told, for experimentation and local knowledge. This will supplement and extend the learning from those. And when we see this example, this is some studies conducted where this is the long-term variability of productivity. That means from 1958 to 2008, when you see there is lot of year-to-year variability of yields. So we can study through modeling what happened in 1978 and what happened in 1998. This way we can analyze, in-depth analysis we can do with the model, because we don't know what happened. We can do with our own data set. Data set will say how this whether that particular year there is a drought in particular stage of the crop, or particular during the growth stages or the grain filling stages, whether there is any fluctuation of weather or other parameters we can study with a well-developed, well-calibrated model. That is the use of that model. Now we will come to APSIM. You just see, this is the APSIM model. APSIM is the Agricultural Production System Simulator. This is the APSIM. It is APSIM. And this is the APSIM model. It is developed by Australia. And basically, you can download this APSIM model from the website www.apsim.info, and you can download this model latest version, because several versions they will modify the versions according to the inclusion of some of the new technologies, new ideas, or new bugs. Suppose they have found out some bugs, they will modify the program like that. And you can download this AppSim simulation model using a simple. You have to enter what purpose you are going to download, particularly for research purpose. It is free of cost. You can download from the public domain. And this is now, earlier it was developed by CSIRO and the University of Queensland, but now they have some initiative, AppSim Initiative AI, under this banner. These are the six universities. They have some collaborative mode. They are working on this called AppSim model, because now they have modified this AppSim tool for the integrated farming system. They are working on it. And you see, AppSim was created to deliver a solid platform for modeling cropping or farming system performance over time. Because for cropping system, we need to model two crops simultaneously. After one crop, the second crop will we need to simulate the second crop. Like that, this cropping system. But at the same time, farming system, we have different crops as well as animal component. We need to incorporate that. So work is going on to model the integrated farming system, and equal emphasis on crop and soil dimensions of agricultural system. This is incorporated in the APSIM model. Equal importance for crop as well as soil dimension. It has the capability to comprehensively simulate management options and a better software engineering process to achieve the above. And this is the advantage of AppSim. And the main concept, the central concept of AppSim is the soil. The soil provides a central focus in the AppSim. Then crops, seasons, managers. Soil is the permanent one, and crops, seasons, and managers will come and go. It will move. So, and finding the soil in one state and leaving it to another. This is the concept behind AppSim, because here soil is permanent. Other variables, that crops, different crops we can grow in the same soil, and the crop seasons, managers, it will come and go. And because here the advantage is of AppSim is there is a nature of plug-in or a plug-in concept. That means, suppose you want to incorporate one management practices, simply we can take that particular management aspect and we can plug into the our modeling framework, our simulation model. That is the concept behind AppSim. That is plug in this property is there, so that. And you see, this is the basic concept of any model. It is the common one. You see, the concept is the soil is there. We can runoff and erosion will be there. It will distribute it into the soil, and there is a deep drainage, and there will maybe the movement of infiltration as well as in the upper layer. It will be runoff or erosion will be there. Then after putting these seeds into the soil, it will slowly germinate, and then the roots will grow, and it will uptake the nutrient from the root zone and the water uptake, and also that slowly the crop, the leaves and other growth stages will come. And they used it will use the solar climate variables, and it will have the photosynthesis, the synthetic activity, and based on that the leaf area, biomass production, everything will be there. Finally the harvest, and it will also give some organic matter into the soil if we incorporate the root zone, roots, as well as if you crop residue also incorporated, then how much soil organic carbon we have incorporated into the soil, and there is a leaching and decomposition of all the livestock manures into the soil. All these are complex processes. These processes incorporated into the model, and we can take one component, one process into the model, and we can study and what are happening into the soil and what is happening into the atmosphere, what are the interaction, everything we can study. And these are the crops and pasture or tree modules available in this APSIM. And some of the component, the APSIM group have some collaboration with other international organizations like IRI, Wageningen University, and other international agencies. And you see, and already I told that these are the important processes involved in this. The features are mechanistic growth of crops, clusters, trees, weeds, and the dynamics of populations, key soil processes like water uptake, solutes, NP, carbon, nitrogen, phosphorus, carbon, and pH, surface residue. We can study each process and surface residue dynamics and its erosion, dry land or irrigated systems. We can modify both the dry land system as well as irrigated system, range of management options, crop rotations, then short or long term effects, one or two dimension, that is multi-point dimension in the same field, high software. These are the advantages of this. And also there is a link with the livestock modules like APSIM farm, that is separate module. This is an extension of APSIM model that also we can use. And as I told, this is a plug-in pull-out modularity. This modular structure of the APSIM is having larger advantage under small scale farmer conditions, because in our field we can incorporate, you see, crop A, crop B, we can incorporate, we can make and output also field management, soil, or these are the separate one we can plug in to the our simulation system. That is the advantage of this simulation APSIM model. And these are the plants already told. This is plant and animal component available with the this simulation model, APSIM model. And you see the environmental conditions, also metadata, then soil, water, sim. These are different modules available in the AppSim. And when we click the different processes, you will get the script of each parameter, or how it calculated, and even if you can move in-depth analysis by modifying the script also, that also we can do. And management file is there manager, how to sow and how to harvest. We need to tell the model when to harvest, that means how to harvest and follow or tillage, etc. And irrigation, how, when we need to give irrigation, how to, when to apply fertilizer, how much we need to apply, everything we need to give. But the real power of AppSim lies in the flexibility of manager module. As I told, the manager module, that means it is flexibility is there, easy to provide a true depiction of farmer behavior, a unique feature to AppSim based on a simple if then else command. This command, basically a pattern command, if then else. This command is there. Using this command, we can modify the script, the manager specification, we can modify the language executed on a daily basis. And it allows simulation of very realistic dynamic adaptation scenarios which other models cannot achieve due to more rigid management specification requirement. Because in other models we have to simply select one, but here we can modify the script according to our situation. Then, for example, you see, for specifying alternate wetting and drying water management condition, that also we can incorporate into the model. Suppose you are putting this management practices, we can make the model, we can make some small script, and we can put it, we can plug into our simulation, it will work. And in a long-term continuous simulation, changing varieties on a year-to-year basis. Suppose 5 years one variety, after 5 years another variety, like that we can modify the model simulation, because there is possibility of, because suppose you have an experiment, long-term experiment of 50 years, in between there may be new variety, we want to incorporate new variety, that also possible with this. And changing fertilizer top dressing rate depending on current in-season crop performance. And we can modify in between the crop dressing. Suppose previously there is a lot of nitrogen is available, we can modify the fertilizer, current fertilizer rate as well as this thing. Then deciding annually whether to this is graze or persist to harvest with a crop depending on the accumulated by this is the foreign state. And this ability for detailed scenario specification is an extremely valuable of feature in a model for assessment of real adaptation options. We can study the adaptation options under different management practices. Whatever management options or decision points a farmer can envisage, they can be described and simulated in APSIM using the if then else application. You in APSIM, just I will tell you, using AppSync, there are four processes are there. You see, first stage is parameterization. That means we need to measure and collect all the parameters. That means soil, climate, crop management to adjust AppSim to local conditions. This parameterization is very much needed. We need to collect all the parameters required to run the model to adjust the model with the local condition. Then calibration. The calibration, what we will do, AppSim said as an experimental trial. We have some experimental trial. We need to see the simulated and observed results are compared, whether both are within the statistical limit or not. We need to compare both simulated as well as observed. Then the empirical model input parameter, that means phenology or soil adjusted until observed and simulated results are similar. We need to see whether both are same or not. Because in these models, one thing is there, genetic coefficients. The genetic coefficients for APSIM also there, other models also there. This genetic coefficients, it is the variety dependent, and we need to modify according to our experimental data we need to do. That is a calibration. And suppose if we use 1 year data for calibration, we need to see whether it will work for the next year, and then accordingly we need to do the validation. Validation means APSIM run against independent data, that is separate data, and in the new season at same site or other local trials. And we need to see the simulated and observed result we need to compare, that is validation. Then after one model, suppose APSIM model, you have well parameterized, calibrated and validated, then the same can be used as a tool for as a research tool. You can use for risk management, yield forecasting, or climate change study analysis, or other all studies like testing of management practices, testing of crop residue management practices, whatever you want, you can study after parameterization, calibration, and validation of model. These are called scenario analysis. Then, so using AppSim, that means you see some of the photograph, we have tried to collect the soil parameters at a different depth, particularly bulk density and all the soil chemical, physical parameters we need to collect from the experimental site, and we need to put into the computer on this modeling model to parameterized model. And this is one photograph of our group. We have gone through the training of APSIM at the SARC Australia Center, and our group is working with the expert there. And another thing is this model, because these models are developed in Australia, and most of the parameters normally we will tell these are developed in Australia, how it will be useful for India. So this was tested and validated by different group and different places for different crops. And you see in Bangladesh, India, Cambodia, and Laos, they have a rigorous parameterization, validation, using site-specific characteristics, site-specific physical, chemical, as well as biological data set they have collected, and they did this testing and validation rigorously, and it was published in several international journals, and it will be available in the public domain of APSIM website. And just I will tell you what is the scenario analysis. You see, using long-term climate data in association with a validated model. Suppose you have the validated model, we can using simple long-term climate data, we can simulate the previous years this yield data. We can simulate, and we can study the crop weather relationship. Also, we can study using the APSIM, and also we can see which are the management practices suitable for that particular area. That means different scenario analysis we can do. For example, suppose you want to optimize the irrigation scheduling. Suppose you can see, suppose is 5 irrigation, 2 irrigation, 3 irrigation, 4 irrigation, like that, different irrigation at different intervals. We can do the scenario analysis. Then sort of like a virtual desktop of 5-year experiment, 50-year experiment, we can do different scenario analysis. A model which has been validated and tested is used to analyze a all range of what if questions. For example, what if I used a modern variety? Suppose you want to use modern variety. How you will do the modern variety? If this variety is not at all available, you just modify one genetic parameter according to the GDD, growing degree days, or some degree days, or the maximum grain weight, or some parameters we can modify, and we can check whether this type of variety will increase the yield, or it will sustain under different management practices. That we can study. And which rabi option is best? Rabi crop, which one is best? Rice, wheat, or maize? Already one crop is there. That particular area, farmers are growing one variety, one crop. Whether we can replace that crop with another crop, that also we can study. How can I best use supplementary irrigation? Suppose I am putting one particular area, we need to see under rainfall situation, which or irrigated situation, whether we can reduce the irrigation amount, or under rainfall situation, with one irrigation, one supplementary irrigation at the critical stages of a stage of a crop will increase the yield, or at what time we need to irrigate. This can be simulated. What if I sow earlier, or try for the second rabi crop? How many years would I be successful? So these risk analysis we can do, and these are called scenarios. So such scenario, well calibrated model can be used for any scenario analysis. Particularly as an agrometeorologist, we can do the scenario analysis. You see here, this is on one example. You see, this is a data set 1957 to 2010, under this much years, what 54 years we have compared the production. There is some years there is yield is very low, and then we have compared with different irrigation. One is flooded situation, another one is control situation, and another one is 80 centimeter, 80 millimeter irrigation, 120 millimeter irrigation. Like that, we have incorporated the management practices and found out how will be the yield level or gross margin, whatever, what different parameters we can convert in yield as well as the net returns or gross returns, anything we can do with this long-term analysis. And when we see what if questions, which crop to sow, when to sow, how much nitrogen fertilizer to apply, optimum maturity length, optimum planting population. That also we can do. Suppose planting population, we can modify the plant 2, 3, 4, like for rice. In a particular hill, we can modify the number of plants in the plant population. We can modify whether it really increase the yield or not, and effect of amount of soil water at sowing. So then what about what are the optimize, we can optimize the soil water requirement at soil, then effect of soil water holding capacity, effect of different southern oscillation index phases, because even we can study the rice growth as well as the seasonal pattern, basically El Nino years, what is happening in the rainfall pattern, that also we can study using the distant models. Then minimizing time to adoption for new technologies. Suppose you have one technology. Suppose you want to test one management practices in your location. Suppose, and you have the model, calibrated model is available with you. You can easily, we can do the analysis, scenario analysis, easily and within a short period of time. Otherwise, suppose you want to test the management practices in your place, it will take 3 years for one management practice, another 3 years. So it will take time, your time as well as manpower requirement, our budgetary financial provision. So it is a costly affair. So well calibrated model can be used for these conditions. For introduction of new varieties, introduction of new technologies, we can conduct the virtual experiments using this computer uh, simulation models. We can use models to help prioritize your options to test in the field and conduct more target experiment. First, we can do the analysis using model. Then we can prioritize your research questions, and then after that we can test in the field in your experimental site, so that we can reduce the budget. For climate change scenarios, it is not possible to directly conduct the climate change scenario or carbon dioxide scenario, that means increase of carbon dioxide scenario in the field. That means there we need to construct big tunnels or open top chambers to conduct the field experiment, and also it is costly affair. If you use the modeling tool, then we can do the analysis within no time. Provide time efficient learning experiences which can minimize the time to adoption for new technologies and allow easy assessment across different locations and environment. That is possible with the model. Then you see, these models we can use it for upscaling of experiments. That means from plot level to country level or regional level, we can use these models. And also this point data, we can use, we can convert this point data into the national level or regional level using it can using GIS platform, geographical information system. If we link these things, we can excuse me, convert these into the spatial different spatial scales. And also now we will talk about climate change studies. You see, the climate change studies, the adaptation options are being examined that have potential to help farmers better management or current variability or risk or future variability. All these things we can incorporate, and how it will be immediately affect the livelihood benefit to the farmers, that also we can study. You see, simply we can modeling is one aspect, and we can link this crop modeling with climate change scenario analysis. Then we can link it with the livelihood of the farming community, so that we can apply these tools to the farm level. That is the beauty of the modeling too. Then these are the APSIM data needs. You see, for parameterization and calibration, these are the data sets required. One is climate data, that means yearly data, suppose you want. Then yearly data, daily data, solar radiation, sunshine hours, then minimum and maximum daily temperatures, daily rainfall data. All these data sets are required for APSIM data, APSIM data input. Then research station data sets, basically we need all management activities such as sowing data. Excuse me, 1 minute. Yeah, okay. Example, sowing dates, transplanting dates, all dates we need to see. These are for parameterization, validation, calibration. Then plant numbers, fertilizer type and application, dates, irrigation dates, the amount of water applied, then phenology date, the panicle initiation, flowering, maturity, all data sets we need. And also soil content, water content, and other soil chemical and physical parameters at a different depth. Particularly, normally we need up to 105 centimeter. If it is not there, okay, we can do with up to 45 centimeter also. And because you see, normally for carbon studies, we need up to 1.05 meter. That is required for carbon sequestration studies. So that's why I told it we need at least 1 meter 5 centimeter depth. We need all data parameters, and these are the chemical parameters we need, and also the dry matter at the different stages of crop growth and at the maturity, and the grain or pod yield for each crop we need. And when ponding was done, suppose for rice, when you have made the ponding, and it was there or not, and how much ponding depth and everything we need. And soil characterizations, if these are not already run, these are we need to do for this APSIM data, APSIM simulation model use. Then soil texture analysis, pH, organic carbon, and measurement of bulk density, field capacity, or the drained upper limit, or the crop lower limit. And these can be measured or estimated from texture, or we can do the direct measurement also. All these things we need to do for a complete APSIM model run. And this I already told. And now I will tell you some of the, 1 minute, just excuse me. So Dr. S.P. Yadav, whether we need to take a question now or in the last
Yes, last step. I will take questions, sir.
Last
Yeah,
okay.
yeah. We have
Okay, shall I
questions for.
continue now?
Yeah, yeah. You can continue, sir.
At what time I need to finish?
Actually, your session is, sir, of 3 to 5, and
Okay,
uh,
okay.
yes,
Okay, thank you. I will continue. So, I will now show you some of the studies we have conducted using APSIM. You see, this is applicability of APSIM to capture the effectiveness of irrigation management decisions in rice-based cropping sequence. This is a particular study we have conducted under our SARC Australia project, and it was published in Paddy and Water Environment. Here, what we did is we have calibrated the model with our long-term experimental data, rice switch system, and we have simulated the long-term data, and just we have compared the long-term data, actual as well as simulated data. You see, both are in the same trend when we compare. There is some variation between these, but the trends are same in both simulated as well as actual grain yield for rice as well as wheat. And uh, this is the effect for irrigation schedule on rice and wheat productivity. So what we did is we have one continuous flooding and 2 days alternate wet and drying, 5 days alternate wet and drying, 8 days. Like that, we have compared, and what will be the effect on yield. We found that this naturally the continuous flooding will be high yield compared to others, but the yield penalty, how much is the yield penalty? Because continuous flooding means more water required, and particularly in our part of the area, there is a higher lifting of groundwater. So the groundwater table is low. So we need to arrest the pumping. So we need to suggest alternate water management practices to the farming community. For that purpose, we have tested different water management practices, and we found that for rice wheat system yield, when you see the 2 days alternate wetting and drying plus this is for rice, and for wheat 5 irrigation there is only a 11% yield penalty compared to the continuous flooding. So like that we have worked out, we have assessed the yield penalty under different irrigation management practices, so that based on this we can recommend the farmer, and this is good, only this much yield penalty will be there. Suppose if you have other varieties, we need to test other variety also. Suppose some other variety, then the yield penalty will be less. That also we can study using this. And another study, that is, as I told, under AGMIP, that is Agricultural Model Intercomparison and Improvement Project. Under this umbrella, we have studied the climate change impact using both two models, DSAT as well as APSIM. And also, I have studied the Indian study, another study. We did the integrated farming system also. That also I will show you. And you see, this farming system, just I will explain because our institute is dealing with the farming system. I just to tell you what is farming system. Basically, each farm is a farming system. Each farmer is a farming system. That is the actual thing. You see, smallholder farm systems are very complex. They commonly have several components tightly interlinked. Example, crop, livestock, and this mixed of also they are getting some income from the non-farm income also, or labor investment. This is a complex situation, and they are managed towards the satisfaction of a multiplicity of goals like food self-sufficiency. You see, suppose one farmer is there, he needs this much quantity of food for family nutrition. You see, as per as the Medical Council of India, for a family of 5 members, we need at least 493 cereals kg per year. And for pulses, a family of 5 members need 164 kg per year. And also oil is 49 kg per year. Like that, this much is the requirement of each family or of 5 members. So we need to see the food self-sufficiency at the farm level and also income generation, then risk management. All these systems we need to see. That is, each farm or farmer is a farming system. All depends on this. Everything depends on the resource availability of the farmer and the ecological constraint. Everything depends on availability of the farmers and ecological constraint. How these things can be incorporated into the model along with the climate change scenario. Yes, climate change is happening. We need to incorporate climate change scenario. That is one aspect. That means climate change scenario, you will weather data is there, we can incorporate that. But we need to see the whether the resource availability will be same at present level or future what will be, and everything we need to see. And why it is required, then capture, we need to capture, suppose I want to see the one district, we need to capture the diversity of farming system and better we fit into the diverse farming systems, and we need to see the sustainability aspect also. And we have conducted two case studies that have particularly two approaches. One is the ICR ACMIP collaborative study. Here what we did is we have tried to link the simulation model with economic models, and we found the farm level productivity we have studied. And another thing is under NICRA project we have studied the all farm approach, that is one farmer is having different components, how it can be linked with the simulation model and how we can study, how we can do the simulation, that also we did. And under AGMIP, this is the integrated assessment framework we have followed. Here also we did the experimental data and the survey data and expert opinion to parameterize the model, and we have used the climate data under the different RCPs, particularly representative concentration pathways at 4.5 as well as 8.5. These are the two climate change scenario we have selected, and also the two periods we have used the medium pathway, that is 2040 to 2070. That is the period we have used, and we have used the crop models. Two crop models we have used, DSAT and APSIM. And during this period, I got an opportunity to interact with great crop modelers like, as far as DSAT is concerned, Jim Johns, Ken Booty, as well as Gerrit and Cheryl Porter, and these are the big shots of DSAT model group, and also APSIM group like Don Gayden and Peter Thornburn, and all these are in the developmental group of these models. I have an opportunity to meet with them and work with them. And then the trade-off analysis and minimum data model, that is regional economic models. We have linked the output of crop models with the economic models, and we have analyzed all these things. And this is the general framework followed under our AGMI project. And these are the crop model, climate models. You see, we have used 29 GCMs. 29 GCMs we have used, and we have generated the climate change scenario under RCP 4.5 and RCP 8.5 for Meerut district. And we also used other districts also, but I am showing only Meerut district. And models, DSAT and APSIM, and the economic model is this. This is also Excel based model, economic models. It is available in the public domain, particularly the university, the trade of analysis. If you search, you will get the trade of analysis, this model free of cost. And this is trade of analysis model. Basically, this was developed by Oregon State University, and this represents the oil farm production system. And here, the output of the crop simulation model are the input of this model. You see because you see the climate model is okay, one part, climate model, then crop model, then economic model, so that the application of climate to the farm level. That is our motto. And trade-off analysis and minimum data is a model of the farm population, not a model of an individual or representative farm. These are the economic say, properties of this trade-off analysis and minimum data set model. So we have used this model also, and under this, these are the four set of questions we have answered. One is, what is the sensitivity of current agricultural system to climate change? You see, current agricultural system means what? At present, this is the agricultural system followed by the farmers. What is the sensitivity of current agricultural systems to climate change? And second is, suppose under current agricultural system, suppose you have incorporated the adaptation strategies, what will be the benefit? And what is the impact of climate change on future agricultural product? Then current agricultural system, future agricultural system. There may be change. After 40 years, what will be the agricultural system? That also we need to see. This is called RAPS. We will call in a climate, we will see RCP, representative concentration pathways. For agriculture, economic world, that means future agriculture. What will be the future agriculture? That is, it is called RAPS, representative agricultural pathways. This is called. So, what is the impact of climate change on future agricultural production system, and what are the benefits of climate change adaptation in future? That also we need to answer. So, this is the rationally behind this diagram. When you see the diagram, the blue one, you see this is the current production system. Because of the climate change, the production will decrease. But because of incorporation of adaptation mechanism, we can increase the productivity to higher level. This is the current production. But when we see the future production system, after 30 years, you see this is the current level of production. But in future, because of the agricultural development, it will move to this level. But because of the climate change at that time, the production decreased to this level. And using some future adaptation strategies, we can increase the production to this level, that is green mark. That is the beauty of this integrated assessment. So all these four questions we need to answer. So we have conducted this experiment in our Meerut district. We have collected 100 farmers spreading different area and different socio-economic background, and we have collected survey data basically for crop management aspect and socio-economic aspect. All these aspects we have collected, And this is the farming system, is the schematic diagram representing the farming system followed in this particular area, that is rice wheat, sugarcane wheat, and this is the major cropping system in this part of the area, and minor crops maize and sorghum. And this is the how the household, that means how some small farmer, what they will do, what are the how the flow of different component in the farming system. Then these are the GCMs we have used. 29 GCMs I told. These are the names in the alphabetic order and numeric letters, 29 models. But we found that some of the models there is we have removed from our study because they are not explaining the monsoon scenario, because some models are developed, all these models are global models, so some there is a lot of variation of rainfall pattern during the monsoon season, particularly more than 200% variation. That's why we have removed these six models from our study, and we scaled down to 23 GCMs. then then 23 models are there. Then what we did, out of these 23 models, some models represent hot, wet season. Some may be hot, dry season. Some may be cool, wet season. Some may be cool, dry. So we have classified these models into five subsets. One is medium of that. And like that, we have arranged these models in different quadrants. You see, this model, suppose for RCP 4.5, 23 mid-century period, 23 models. In these models, we found that this season, hot wet season, there are four models represent this. But out of this, we have, this is the mean of this, and we choose one model which is close to the median. So we selected M. This model we have selected. As far as this quadrant is concerned, we have selected S model, SGCM. Like that, we have identified five GCMs which represent different climate system. That means hot bed system, hot dry system, cool dry system, cool bed system. So that we can put some, we can do the scenario analysis using different GCMs. And similar way we did for RCP 8.5 for the same period 2040 to 2069. And when we see the yield data, mean monthly growing season. You see, for the particular rice season and wheat season, how these climate change scenario, this is the average value of that temperature, maximum temperature, mean temperature for that particular season using this model. That means baseline data, that suppose for example, baseline data shows there is a for 34.8 degree temperature, average temperature, maximum temperature during the rice season. But at the same time, M model shows it is 37.1. So there is 2.3 degree increase of temperature under hot, wet climate. Like that, we have calculated the climate average of that particular season, rice, wheat, as well as annual season for different climate scenarios for RCP 4.5 as well as RCP 8.5. Similar way, we have calculated the minimum temperature during the crop season compare and then compared with the baseline data. And when we look into this, the hot season generally, normally this is the higher temperature, minimum temperature during the this quadrant, that is hot and wet climate scenario. Like that we got for the both 4.5 as well as 8.5 RCPs under 2040 to 2069. And here also, this is the monthly variation of different parameters as well as seasonal. And as far as the rainfall is concerned, when we look into there is lot of uncertainty. That is another factor, uncertainty. You see, the climate change itself that is a uncertainty. So when we talk about temperature, there is not that much uncertainty. But at the same time, rainfall is concerned. When we see the rainfall, there is lot of variation between the mean as well compared to mean as well as the projected scenarios. Lot of variation among the different months, but overall, when we see rice season or wheat season, it is okay. But at the same time, there is large scale variability, uh, particularly monthly variability is there. Then these are the abstracts of farm survey. We found that. You see, this is the general condition of the farm, and these are the holding size, wheat grown area, average land area, rice variety, what variety they have used. This is the variety, general variety we have selected. There may be more varieties. This is the variety which is maximum farmers using this variety. And this is the spatial variability among the 100 farmers. This is the spatial variability of management practices and the yield level. The spatial we have compared using the GS platform. This is the spatial variability of rate of transplanting, harvest, number of irrigations, and grain yield. For rice as well as wheat, we have compared, we have used. And another thing is we have compared the simulation. You see, when we see the model, the first graph, you see this is the simulated using DSAT as well as APSIM and observed value. Observed value means from the survey data as well as we have compared. So when we compare this, there is a variation between this model output as well as the observed value, because you see this will be there, the observed value, because there is we have used calibrated the model at the experimental site. Then we are using this model for farm level. There we have used we don't have maximum minimum data set, only limited set of data is available. That's why we have observed this much variation. But when we see during the wheat season, there is lot of variation between the model output and the input. And based on that, we have modified the genetic parameter before doing the climate change analysis at the farm level. Because you see, at the your experimental site it is okay, but when we move to the farm level, then the scenario will be different. That condition we need to incorporate into the model by modifying the genetic coefficient, and then we have matched with the actual yield as well as simulated yield under both the models. Then, when we have studied the carbon dioxide sensitivity of wheat at a lower level as well as higher level of nitrogen under both the DSAT as APSIM. I am just comparing this, the carbon dioxide level in both the models. You see, in both the models, you see the carbon dioxide at a high level, that is 180 kg nitrogen if you put, then both models shows at par. But at the same time, at a lower level, the model output is different. That means the sensitivity of both the models are different. Like temperature sensitivity of wheat during using DSAT and APSIM. Here also there is lot of difference between both the models. After some level, after 2 degrees centigrade, there is lot of variation. This is sensitivity. Then rainfall sensitivity, there is not that much sensitivity of rainfall, because in both the situation we are following the irrigated situation. That's why. Then fertilizer sensitivity, just we have used our farm level data. What is the sensitivity after modifying? You see, almost both the models follow the same sensitivity. That means both models parameterized under very well calibrated parameters. We have calibrated this model under good condition so that we can use this model for climate change analysis or scenario analysis. And you see, we can, as I told earlier, we can study the understanding current agroclimatic variability also. You see, from the long-term experiment, we have studied what is the actual data set and actual what is the simulated data in both the models, and also the growing season maximum temperature. You see, the growing seasonal maximum temperature, it is increasing by from recently, and there is a decrease of wheat yield at our place. So because of, you see, the increase of maximum temperature during the crop growing season, particularly in March and April, and it will affect the grain filling stage, and there is a reduction in the size of the size of the grain, and there is it will affect the total grain yield. And for particularly wheat season, you see, this is the trend level. And as I told, the uncertainty, you see, I told there is this much climate change scenario. So when we talk about the climate change scenarios, what is the uncertainty in climate change? You see, the models spread over the growing season maximum temperature under different models. It is from 27 to 29 degree. So almost 2 degree variation is there for growing degree maximum temperature. For minimum temperature, that also it is 2.5 degree difference among the models. You see, that also we have studied. And you see, these are the data sets we have used for our calibration and validation of their model. These, as I told, these are the data sets we need for parameterization, calibration, and validation of the model. And these things we have collected from our long-term experimental data. As I told, these are the genetic coefficients we have used for this particular variety, PBW343. And these are the, for APSIM, these are the, 1 minute, these are the parameters we have used for uh, our calibration. You see, these are the cultivar potential grain filling rate, then grain per gram per stem, and the end of juvenile period. What will be the growing degree days? Then floral initiation unit, flowering unit, start grain fill unit, maximum grain size, like that. These are the genetic coefficients we have used for APSIM simulation, and this is for DSAT simulation. And as far as the output is concerned, you see the output under different climate change scenarios, and under different models. You see here, red is APSIM and blue is DSAT. When we look into this, both models, there is difference between these two models, and so we can use this. These are the range of values from the model. That's why we have used for rice. There is a, when we talk about rice, when we talk, this is hot and wet season, this is the max increase of temperature. So here you see one model shows there is a only limited degree of decrease, on average, but at DSAT shows there is a decrease of this much percentage. But overall, when we you see in some farm, they have management practices different, so there the yield will be higher. But in some places, the yield there may be negative. For the hot and dry season, when you see the naturally the yield will be less compared to other scenarios. Like that, we can assess the climate change impact on rice yield as well as wheat yield under different representative concentration pathways. That is the, and we have compared rye wheat. Here wheat also, there is a high reduction when we see the models, hot season, dry season, how much the yield decrease. There is almost 20% in some of the models, some of the scenarios. So like that we can calculate, we can assess the yield decrease under wheat season for different GCMs. And for rice also, under RCP 8.5, we have calculated there is around 10% decrease in yield under APSIM, but it is around 6%. Though that means 6 to 10% decrease of yield under rice irrigated situation under RCP 8.5, that is under hot dry climate without any irrigation, without, there may be irrigation different, but with the assumption that there is no dearth of water for irrigation under future situation. So under RCP 8.5, when we look into this, in all GCMs, that means hot wet GCM, cool dry season GCM, hot dry GCM, cool wet GCM. In all the GCM, there is a decrease of yield under climate change scenario. That is 8.5 RCP, representative concentration pathways. That is the high level of this solar radiation or carbon dioxide content. Then this is the output of climate change, that is a cropping model, cropping simulation model. We will put this output into the trade-off analysis and minimum data set model. Here we need some of the data set, particularly the socio-economic composition of that area. And we have collected through the survey as well as the secondary data. And we have put all these data set, particularly yield, price, variable cost, net returns, and the standard deviation of net returns, farm size, family size, like that all component we have calculated, we have estimated some of the parameters, and also from the secondary data as well as the survey, and we have incorporated into the model. And one more thing is, this is okay, survey data. Then there is one pyramid we have followed. We have surveyed the farmers, then we discussed with the researchers, then we discussed with the agricultural developmental agencies, universities, progressive farmers, and then at the national state level, then at the country level. We have discussed these things, and also we have collected some of the literature regarding the future agriculture. That means basically we did all these interactions, stakeholder interactions, for this RAPS, that means representative agricultural pathways. It is nothing but how we will visualize the future of agriculture in 2050. That means my vision will be different, my visualization will be different. As a scientist, as a developmental official, his visualization will be different, and we bring all the stakeholders in single platform, and we discussed with them, and we arrived a common, we have discussed with several, you see, at the university and at the farmer field, and with developmental officials, like we discussed with IMD as well as other agencies. And finally, we have found out the different pathways for the future. This is the sustainable pathway for the future. That means in the in future 2050, what will we do? Better management of natural resources, so that the government policy is more allocation, then less degradation, that means more allocation for natural resource management, then less degradation will be there. The farmers will realize long-term gains from the efficient resource use. We need to use the natural resources efficiently, so that we can reduce the degradation. Then low cost of production, that means efficient use of on-farm resources. Then sustainable mechanization. Slowly mechanization is increasing. That means sustainable mechanization will be there. Then high-tech agriculture, then higher energy efficiency. Then low income disparity among the farm and the farm labor gets good employment in rural area. So the region becomes food secure on sustainable basis. This is green agricultural pathway in 2050. And another pathway is pessimistic pathway, that is gray agricultural pathway. Here there will be high population growth, agricultural intensification, higher exploitation of natural resources, declining land productivity, outmigration of laborers, more allocation of subsidies and crop insurance, high market and climate risk. This is a pessimistic scenario. So under these two conditions, how the policy, socio-economic, policy, institutional, and socio-economic conditions will change. We have discussed with the stakeholders, and we come out with whether it will decrease or whether it will increase in future, and what will be the value, that means 10% increase or 20% increase. We have discussed at the different level and also collected through literature, and then we have quantified and we have incorporated into the model, and we have also incorporated the adaptation package for simulation as well as for the economic model. That means advancement of date of sowing, that is 1 week to 2 weeks from the present, use of short duration varieties for rice as well as wheat, and back it into the model. Then these are the key messages we got through modeling. You see, the climate, annual rainfall projected to increase in most of the models. Then the temperature increase more in wheat season compared to rice season. By 2050, the maximum daily temperature could increase by 1.5 to 3 degrees. And like that, we have found out the key messages from regarding climate, then impact. You see, rice yield will decline by 12% and wheat yield by 24% in 2050, even with recommended irrigation. Net farm returns decline by 14% and per capita income by 9% under hot, dry climate scenario. 74% household in the district will be vulnerable to climate change in 2050. And these are the impacts. Then adaptation. If you incorporate the adaptation mechanism, then yield can be increased by 13%, and the net farm income can be increased by 17%, and per capita income by 10%. And because of the adaptation package in future, we can make the farmer 53 to 60% for sustainable development pathway, and we can adaptation rate we can increase by tested adaptation package. This is the key message from this project. And these things are available in the website. If you go to the www.agmip.org, you will get all this data set. Even full data set is available. You will get it. And these are already I told, these are the APSIM. As I told, there is a irrigation. You see, you want to put this if and but, if else then. These are the scripts we have used. You see that alternate drying and wetting. For that purpose, we have developed our own script and incorporated into the model. Then another thing is indicated time is 4:30. Okay, anyway, 10-15 minutes I will complete. Then this is a integrated farm modeling. This again second approach. This approach under this methodology we have used the APSIM, which is particularly the extension of APSIM model, and we have used the 30 case study farms in and around Mirror district, and we have this is basically here, the earlier we have conducted this different places with one survey. Here it is, we have created virtual farm in computer. Means 30 farms, virtual farms, really we have created in the computer. And based on, and then we shown to the farmers, this is the output of model, and this is the under future scenario this will happen. Then what type of adaptation you want to incorporate, they visualize their future, and we have incorporated that also, how it will be. Then this is the basically an iterative process. Means one day process is not there, it will take long time, and we have completed this process in 1 year with different interactions with the farming community. And these are the simulations we do. The all farm household configuration of APSIM, that is called apps farm. Then examine all farm resource allocation questions, how much area allocated to different resources, different crops. Then baseline model of a smallholder farm created using APSIM simulation setup. Then what is the percentage of minimum percentage main crop on the farm that provide food security in 90% of the years? How would this change if fertilizers are used? How management practices will incorporate, how it will be, how much area we need to modify in 2050. And this is the schematic diagram of this model. And you see, this is a generalized schematic representation of one farm. It's a family. They are growing rice, black gram, wheat, fodder, sugarcane, and they are putting FIM into the field. They have the buffalo and the cow, and some of the crop output will go to the market. This is the schematic diagram of one farm. And we have parameterized the APSIM farm, as farm, and through dynamic simulation model we have created the virtual representation of each model, and we have asked the farmer to agreed upon the model output in terms of crop yield, growth, margin, profits, and their variability. And after agreement with the farmer, after creation of simulation setup, we have run the model for baseline as well as different RCPs. Then these are the characteristics of 5 farms. I will show you 5 farms. You see, first farm, it is having the area of 2.4 hectare. Irrigation source is tube well. These are the crops they are growing, and this much area allotted for each crop. And rabi crop is this thing, and crop livestock. Livestock is this thing. Like that, we have arranged. And there may be, for each farm there may be 2 type of benefits. One is short term benefit, another one is medium term benefit. The short term benefit, that means short term benefit means more isolated actions that take advantage of opportunities or mitigate impacts. Within short period we need to take action, but long term or medium we will get time to take strategic decisions under different social and with the family for their socio-economic institutional context, because the externality will be there, but at the short term they have to take the immediate step to minimize the risk. And for one farm I will show you, this is the one farm. They are growing these crops: mustard, sugarcane, wheat, rice, fodder, and livestock, and the 2 point area. Under 2040, this will be the scenario. You see, due to lot of variability of monsoon rainfall, they in future they may shift rice area to sugarcane, fodder, or mustard in future. And there is a chance to increase the livestock population because they want to increase the livestock population in future, and for that they will increase the fodder area. And if increase the fodder area means they at the cost of rice or sugarcane area, since because for most of the years there is a wheat yield is affected due to climate variability. They may plan in future they will shift from wheat to sugarcane or fodder, some of the area. So there is no change in mustard area in future because the farmer is using mustard for his own purposes, culinary purposes. Then what will be the impact? You see, the impact will be more allocation for sugarcane, mustard, and fodder. That means water diverted from rice to other crops. Though more allocation for livestock may not affect the other crop directly, but more water is needed from the baseline scenario. What they will do, the, they will reduce the plant available water to 20%. If we incorporated all these things into the model, then this will be the case for that farmer. You see, 17% reduction in profit under baseline condition. But under baseline condition, if you change the production system, but in future, there will be 29% reduction in profit in future. This is the impact of climate change on productivity and by farm income in 2040. Then this is the adjustment. In future, they will adjust the crop area. After adjusting the crop area, they got reduction in 19% reduction in future. But reduction can be minimized by adopting some adaptation measures, some integrated adaptation measures in future for that particular farm. This is the beauty of APSIM. This is the scenario how we can integrate climate change with crop model than with the economics. That means we need to use the modeling framework for application side. This will be yield forecasting, yield level we can, this is yield level simulation. Likewise, we have, this is the way forward. We have not used the livestock simulation. We have simply put this much reduction will be there in the livestock. We need more capacity building activities needed in India for livestock simulation because there is nobody, I think only limited persons are doing for the livestock simulation. Then another study with the APSIM model. This is under ICR University of Nebraska, Lincoln, USA study. Here also we have used APSIM for yield projection, yield simulation for future. Here, this is particularly University of Nebraska, Lincoln, and in India, our institute as well as ICR ICR Indian Institute of Water Management, Bhubaneswar. These two are the partners, and here we have considered five crops, that is rice, wheat, maize, sorghum, and millet, whole millet. These are the five crops we have used all over India. We have considered all over India. We have calculated yield gap of these crops in different weather zones, weather buffer zones. I will tell you what is weather buffer zone. We have used this is basically a world program, global yield gap. Several institutions are participating in this program. And we have myself and another scientist from Indian Institute of Water Management. We both participated in this program. And we have used for maize, hybrid maize model developed by University of Nebraska, and sorghum wheat model, that is Bofost model from the Wageningen University, rice wheat model, rice wheat crop, we have used APSIM model. And these are the models is used and how we have used them. For these five crops, we have identified reference weather station. It is based on the crop harvested area, which suppose we have identified district-wise crop area, which districts cover under maximum area, suppose for rice, maximum area of raise, and then we have identified some area. This area is under, suppose 5 districts are there. These 5 districts under this area, for every 100 kilometer radius, we have assigned one weather station. For that weather station, 100-kilometer radius we have considered. For like that, we have identified climate zones, then crop specific harvest areas calculated, then weather station buffer zone. Then accordingly, we have identified major soil types. Suppose in that particular area, there are 5 major soil types. We have incorporated all the soil chemical physical parameters into the model. Then crop model simulations done. Then we have compared the crop model simulations with the actual yield. Actual yield is the average of 5-year district average data, and accordingly we have calculated. Here we have used no climate change. We have calculated the crop simulations model potential yield. We have calculated. We have used this methodology when we see the production ecologies principle. For any crop, there will be a potential yield without any reduction of any resources, with the maximum utilization of carbon dioxide, radiation, temperature, and crop features. This is the potential yield of any crop. That is, it is variety dependent. Then there will be a limited factor, that is water limited or nutrient limited. Then the yield will be reduced, but actual yield will be less than that. So we have calculated the yield gap between potential and actual. Then this is the yield gap level we have calculated for all these 5 crops according to this protocol, and using these models. And this is for some examples, and yield gap of major food crops. And just I am showing rain-fed sorghum, and this is the yield gap in percentage. This much is the yield gap percentage. I think in each crop we got around 20 to 25 weather zones, weather buffer zones. So 20 simulations we did for each crop, 20 to 25. That is rain-fed crop as well as irrigated crop. We did the analysis. And based on these points I told, in the future challenge for modelers as well as this uh, modeling community as well as agrometeorologists is accurate modeling. You see, the scale, particularly the conversion of micro to meso or point value to higher scale, the spatial adaptability of modeling, crops growth simulation modeling, use of crops growth simulation model. How we can do? We can do with the GIS and all other things. But how it will be accurate? That is a challenge to the community. Then cropping system. All models are cropping system models only. But how we can move from cropping system to farming system, that is also a challenge. Then cropping system models are whether these are friendly. In that case, why people are not using, only limited persons are using for crop modeling. Basically this is a data hungry, and also the capacity, more capacity buildings are required. And also we need to see how it will be more user friendly. We need to see that also. Then how to link with agromet advisory services effectively? Yes, we can link the model, because suppose what you have calibrated one model, APSIM model for your place, and you have the weather data for up to today from growing season first day to 30 days, using the past weather data from 30 to 90 days, we can make the yield estimation. But here also we need accurate weather data forecast is needed. That if it is there, then we can link the agromet advisory services effectively. Then calibration and validation. What people are doing is they will simply put some values without knowing the physical meaning of each calibration factors. That is very much needed, and without knowing the parameter and what the sensitivity of each genetic coefficients into the yield level or at the different physical processes, then only the accuracy will come. More accuracy is needed for calibration and validation. Then collection of input data, it is also a challenge. Then how we can use this for yield forecasting, as I told just previously. Then how we can incorporate pest and disease interaction into the modeling framework. Then development of farming system models, particularly for Indian scenario, it is also mentioned above. These are the challenges faced by the research generation for the future. So we need to see these points into consideration in future. Thank you for your patient hearing, and hope my presentation will be useful for the audience. Thank you for your patient hearing. Thank you.
Okay, thank you very much, sir. And participant can ask their questions and put their question in chat box. Sir, we have received one question
Yeah,
of irrigation provided by flooding methods, but in the model we have to fill the data on amount of water used at different stages. Then how we can use?
yeah. You see, in the model, we can we can incorporate the manager file. You can plug in the manager file and you can modify the manager file according to your situation. That means at the different stages how much irrigation, and also date also we can provide, and quantity also. Suppose flooded irrigation we have to provide. Suppose you are giving flooded irrigation today, you are giving flooded irrigation, then you need to give the water level. We have to measure the water level, that we need to give in the model. Suppose today you have the 2 centimeter, there is the modification, we need to make some modification. Suppose today it is 7 centimeter, yeah, 7 mm, yeah, 7 centimeter water level. Then tomorrow the water level is 3 centimeter, we can incorporate that into the model. That is possible. And also there is a water budgeting method is there. It automatically it will calculate what will be the water budgeting, what will be the water level in the next day. You can verify both actual as well as simulated, and then if anything is there, we can modify that script or genetic parameters. We can do that also.
Yeah, okay, sir. Thank you. And another question: is there any difference between DSAT and APSIM model, and which scenario is suitable for our country, sir?
Yeah, you see, as far as my experience is concerned, you see, DSAT and APSIM both will work in Indian condition, but we need to calibrate and validate the model as per Indian situation. If you calibrate the model, both model will work for Indian condition. There is no issue.
Yes, sir. Thank you, sir. And no more questions, sir. And sir, thank you very much for delivering a nice talk. Actually, I know, sir, you have just recovered from your surgery, and
Yeah.
you continuously speak 2 hours, sir. Uh, it's very nice, and it is very good for our participants, sir. And it was very nice lecture, and I think you did so many work, sir. We can't cover your work in 2 hours, and it was very nice, sir. And we are highly thankful to you, sir, for nice deliberation and accepting our invitation from me and my committee and a participant also. Thank you very much, sir. And now this session is over. Tomorrow session will start at 11 a.m. on application of extended range forecasting to cope with the climate risk in crop modeling by Dr. Kirpan Ghosh, Head Agricultural Meteorology, Division of India Meteorological Department, Shivaji Nagar, Pune. So thanks once again, sir. Thank you very much, Subhash sir. Thank you.
Okay.
Thank you.
Thank you. Thank you for giving me this opportunity. Thank you for your department, all, all faculties and as well as committee.